Yeah, I guess we can just get started. So,
Okay.
yep. Let me, yeah. Hello, everyone. Welcome to today's DDLC seminar series. And we have today Professor Murat from UCB. And before we begin the talk, just a background about Dr. Murat. He did his undergrad in Istanbul, Turkey at Bogazici University, and then he did his master's and PhD at UCC Santa Barbara. And his research is along the lines of control theory, autonomous systems, and multi-agent systems, applications to transportation, energy, and biology. And he's associated with a number of research centers at UCB, the AI labs, Deep Drive, theoretical foundations of learning, inference, information, and microeconomics labs, and a few more research centers. And about a little more, he has received the NSF Early Career Development Award in 2003 and the Donald P. Ekman Award in 2006. And he has received the SIAM Control and Systems Theory Prize in 2007. And in 2012, he got elected as an IEEE Fellow. And he has received Antonio Robetti Young Researcher Prize in 2014, and along with an Electrical Engineering Award for Outstanding Teaching in 2014, and and also an outstanding paper award at the TCNS in 2017, and an Automatica paper prize, IFAC Automatica paper prize in 2020, and he became an IFAC fellow in 2020, and in 2021 received the Brockett Williams Outstanding Paper Award. Now, without further ado, I'll let Dr. Rasa take on the topic. Yeah.
Okay, thank you for the introduction and the invitation to speak here. It's been a long time since I've been at Cornell. I think it was 2008 when I drove by and stopped by at the campus. It was beautiful, but it was June, so I know how it is now in January. But be patient, it will come, the beautiful days. Okay, so back to the talk. So I'll talk about control across skills and applications to traffic management. Okay, I need to advance these slides. Hang on. Too many screens in front of me, so okay, I guess this should work. Okay, so the overarching theme is a holistic view of traffic management, but we will talk about broader things than traffic management. That will be sort of a motivation, and it will be an example all across the talk. So about 10 years almost ago, we submitted this proposal to the NSF CPS program that was entitled Traffic Operating System. So the view was that, just like the internet, we can consider traffic management to be a multi-layer hierarchical control scheme, including the vehicle level control and road link level control, which includes things like the timing of signals, on-ramps and on-ramp meters and that kind of stuff, and the network level control, which includes routing decisions. But the main idea was that we would go beyond just studying things in isolated layers, but also take advantage of information flow between the layers to get the maximum out of the existing capacity of the roadways. Things like, using information from the vehicles for changing the timing schemes and vice versa, using information from the traffic lights for the efficient control of vehicles. So you'll see examples of these now and then, but I will start at the lowest layer, vehicle level control, and then we'll go up to the road link and the network levels. So at the vehicle and road link levels, we'll talk about the main ideas in hierarchical control. I'll tell you a tiny bit about reachable sets, which are critical for the design of safe control strategies. And as part of that project, we we had the platoon demonstration in urban traffic, so I'll briefly mention that. And moving up to the link level, I'll tell you a little about how we do reactive signal control using ideas from formal synthesis. And then at the network level, we'll talk about non-atomic games, which we call population games. Population games also include a little bit about learning of the users along the process and the associated evolutionary dynamics. And we ask questions about whether the resultant dynamics create trajectories that converge to Nash equilibria. Two special types of games play an important role: potential games and monotone games. We'll talk about both, and we'll talk about convergence to Nash equilibria for those special classes. So first, a few words about hierarchical control. So in hierarchical control, we are dealing with multiple layers of decision making. So there is a higher level supervisory control layer and then a low level control layer. The question is, we don't want to ignore the other layer when designing one, and we want to be able to give formal guarantees for the correct operation of the two layers combined. So in one instance of this, we do a finite state abstraction of the continuous dynamics in order to come up with supervisory control actions. So the idea in doing that is to partition the continuous state space into cells or boxes, however you want to partition the space, and treat each one of these partitions as a discrete state. So we use reachability analysis to find the successor states. So given that you start in a cell of initial conditions, right, under a given set of control actions, what are the other states that I can reach? So that's the problem. And that creates a finite state model like the one you see at the top. So this finite model is, because it's finite, it's amenable to synthesis via formal methods. And the advantage of that is we can synthesize controllers at the higher layer that will satisfy, things like temporal logic formulas for requirements. And that way, in our synthesis of the controller, we can go far beyond the traditional objectives of, set point stabilization or trajectory tracking. So when we get guarantees for the finite state abstraction, those carry over to the actual concrete system, because in our abstraction we follow certain simulation relations that guarantee closeness of the behavior of the finite model to the trajectories of the continuous model. So this is easier said than done. I mean, at this level of high-level explanation, it's easy, but there are many computational issues when you actually want to do this. So one of them is reachability analysis, because you have to do this so many times. For each cell, you have to find the successor states under each set of condition inputs, and you can imagine the combinatorial explosion in this process. And furthermore, there are issues about what are data structures for storing these abstractions. There's again combinatorial problems. So to deal with these issues, we've heavily exploited the system structure, sparsity in the system model, and the order-preserving property of dynamics, which, as you'll see in a second, are quite natural in various driving scenarios. And also for reachability, we also exploited system structure as well as statistical learning theory. I'll briefly mention those. So just a few application examples. Using this abstraction concept, we can characterize safe sets in autonomous driving, as well as safe control strategies. The figure you see on the left, I think that's just for a simple case of vehicle following. So you have two vehicles. There's a lead vehicle and there's an ego vehicle behind. So you want to know the set of safe states in terms of ego vehicle's velocity, the lead vehicle's velocity, and the headway we should be keeping in between to remain safe. Here we are basically accounting for the worst case scenario where the lead vehicle starts braking So are we safe in the sense that if we also start braking, we're going to avoid a crash? So how do we precisely characterize the safe set? So the abstraction helps us with that because it's when our requirement is safety, we get a safe set in return from the process I described. We also, along with the safe set, we get safe control strategies, those that keep us away from a collision. So one thing I want to emphasize here is this approach to hierarchical control design may not be to everybody's taste, but the safe sets we generate can be used for other control strategies as well. For example, you can take the safe set that you see in the picture, and you can incorporate this as a constraint into a model predictive control algorithm. So we've been doing that rather than using the safe control strategy generated by the abstraction process. Oh, and by the way, the two figures you see on the left, there are two safe sets. One is a relaxed safe set. So here we're saying it may be way too conservative to plan for for the guy ahead of us braking instantly. And so we can relax our safety definition as a mild collision where the velocity differential between the two vehicles is below a certain threshold. So it will be basically a fender bender type of collision. So all of these can be incorporated in this framework. Okay, so in addition to these finite abstractions, we also have pursued the notion of a continuous abstraction where the abstraction is still a continuous space dynamical system, only it's simpler. Simple enough that you can do real-time planning with it. Perhaps it's a linear model that you can incorporate in MPC. So again, we use simulation relations between the abstract and the concrete models so that their behaviors remain close together. And we also account for the error in this process as guided by the simulation relation. So if you have a reach avoid type of scenario, what you'll have to do is you'll have to take into account the tracking error that will result from this continuous control design. And then you'll have to bloat your obstacles and shrink your target sets by that margin so that despite the low-level controller's error, you'll be able to meet those requirements. Okay, just a few words about how we compute reachable sets. First of all, reachability, as I said earlier, is critical for the abstraction process. Or even if you design the controller by other means for safety certification, you still need to do some reachability analysis under, a set of disturbances, a set of initial conditions, and a set of parameter variations. What can I over approximate my trajectories so that I know they don't intersect with an unsafe set? So we've done quite a few different things for estimating forward reachable sets. In our earlier work, we used monotonicity properties, but more recently, so the issue here is we're using sample trajectories, right? And we see where those land. And from those samples, we are trying to infer an outer bound for the actual reachable set. Of course, there are a bunch of trajectories we have not simulated in between, right? So essentially, we're trying to generalize from the samples to initial conditions or parameters that we have not seen yet. So in a statistical sense, you can call this a generalization problem. But in our early work, we did not use any statistical reasoning. We just use properties of the dynamical model. So we use things like monotone systems theory and contraction theory. Contraction means the trajectories between the distance between two trajectories can be bounded because by some inherent contraction property of the system. Monotonicity means there is some order preserving property in the system. So if I have two samples, all samples that start in between in a box whose extreme points are those two trajectories can be sandwiched between those trajectories. So we use these dynamical systems concepts, and the results were summarized in this in this book, a very short book that was meant to be written for accessibility more than comprehensiveness. So it's a good resource if you are interested in that line of work. But as we were working on this book, we came to realize that we can do a lot more if we also use concepts from statistical learning, such as pack learning, probably approximately correct learning, to generalize from the samples to trajectories that we have not seen. So the problem with this approach, though, is we use absolutely no information from the model other than the ability to generate trajectories. So our most recent work deals with what we can do if we know something about the model, but we're also trying to incorporate what we learn from the data. And for that fusion, we've been using Gaussian process model. So that's our most recent line of work. Now, with that, I'm going to move on to our platoon work in urban traffic. We did a demonstration as part of that project I mentioned at the beginning in Southern California in a stretch of road about like 2.5 miles. The reason we were there is because the traffic lights there were equipped in a way that they could communicate with our vehicles. So platoon demonstrations have been done before on highways, but those were early demonstrations, and they used dedicated roads, dedicated lanes, marked with magnetic markers and things like that. So here we are completely out in the wild. We have no control over what's happening around us. So we have these three vehicles. We had these three vehicles. They are no more. And so we are keeping 6 meters between the vehicles and 6 meters from the beginning to the end, even when you're accelerating. So we start at the red light, 6 meters apart, and we accelerate to 45 miles per hour, which is the speed limit, maintaining that distance. So initially at low speed, 6 meters is quite comfortable, but when you reach the speed limit, it gets pretty spooky because this is serious tailgating. But nevertheless, our controls were able to keep the cars safe away from collisions. So our initial plan was to use 4 vehicles. That's why the figure is showing 4 vehicles. But then budget and other constraints limited us to 3. So we have 1 lead vehicle and 2 followers. And the figure at the top in the middle is illustrating the communication structure. So we did these experiments just before the closures due to the pandemic. So in fact, if we had waited another week, we wouldn't have been able to do this. It was cool. It was interesting with the students. We had some scary moments, but worked well. So from that, I'll move on to the road link level and say a few words about how we do reactive signal control. So our goal here is to express the finite horizon goals for traffic, such as dissipating queues, avoiding saturation, and so on, using temporal logic. So the main point here is to move away from asymptotic behavior, which is what typical software for tuning traffic lights, their timing is based upon. Synchro is one of those popular tools. And it's basically based upon a steady state assumption. So our goal is more to deal with transients. So I don't want queues to build up, or I want to dissipate queues that exist, avoid saturation and things like that. Things that I can express in temporal logic. So if I do that, if I express my goals in temporal logic, then I can turn to reactive synthesis for software verification, from software verification. So all I have to do to be able to bridge the two is to be able to express the flow dynamics, which are typically written in continuous space, even though so you almost view this as a continuous fluid flow, right? So the states are continuous, and we represent this with a discrete model, again by chopping up the state space into different bins in this case. And these bins are easy to interpret. So the different axes are different flows on flow rates on different road segments. So a box that's on the lower left corner would mean, low density on both lengths, right? Um, a, a box on the upper right corner would mean highly congested in both lengths and so on. And based on where you are in these state spaces, which box you fall into, you'll get a certain signal timing strategy to deal with it. So we summarize this in a paper that was published in the Control Systems magazine in 2017. We also took this opportunity to give a little primer on temporal logic, finite abstractions, and the reachability tools that we used for that purpose. In fact, the results on reachability using monotonicity came out of this study of trying to deal with traffic flow, because a lot of these continuous flow dynamics have an inherent monotonicity property, or a variant of it that we call mixed monotonicity. And we were able to generalize from this example and create a much broader theory that's applicable in other domains besides traffic. And finally, I'll tell you a little bit about what we are doing at the network level. And here we deal with non-atomic games because it would be inconvenient and almost impossible to deal with, modeling vehicles one by one as players. Instead, we look at a continuum model again for large numbers of agents. So here, instead of keeping track of individual vehicles, we look at fractions of vehicles that use different strategies. So in the case of congestion games for traffic flow, the strategies are basically the routes. So you may have a certain origin-destination pair, and the different routes that connect them would be different strategies. If you assume an inelastic demand, assume that a certain number of vehicles have to make that trip from the origin to the destination, and that's not negotiable, then the sum of those ratios, or the sum of the flows, have to be fixed. That means your space is a simplex in the space of fractions of strategies, or the flows by strategies. So a little brief history about population games. So the equilibrium concepts, the Nash, what we now call Nash equilibrium concepts, actually go back to 1950s, almost concurrent with the development of Nash's work. So Wardrop in 1952 and Beckman and co-authors in this book that you see on the right in 1956 developed user equilibrium and social equilibrium concepts, and they made no effort. In fact, they probably were not aware of the work of Nash. So there is no mention of the word game in any of these works. They basically use optimization to formulate their concepts. The work of Nash was concurrent, and later others made the connection between them. So most of you, I'm sure, are aware of the Breas paradox. So that appeared in 1968, and there have been a number of other studies on the disconnect between the Nash equilibrium, which results from selfish behavior of the users, and the social optimum, which would have minimized the total travel time for everyone. So later on in the 1980s, evolutionary biologists, most notably John Maynard Smith, tried to adapt game theory to evolutionary dynamics. But now what we're seeing is a confluence of all of these. So evolution is no longer something we associate necessarily with biology, but rather we think about how the users adapt to different strategies, how they change their strategies, and what is the evolutionary dynamics resulting from that, not the evolution in the strict biological sense. And then there are questions such as, do these evolutionary dynamics give us trajectories that will converge to Nash equilibrium? All right, so in these games, I mentioned a simplex for fixed demand, but you may have multiple populations. In the case of congestion games, each population may be determined by an origin-destination pair. If you have multiple origin-destination pairs, which you do, then you have to treat them as separate populations. Basically, the assumption is that within a single population, the users will be identical. Their behaviors will be identical, their goals are identical, and the strategies available to them are identical. If there are discrepancies, they have to be split off into different populations. For each population, you're going to have a simplex describing their behavior, because the sum is a sum over the whole set of strategies is constant, and their Cartesian products will be your overall social state vector. And the cost, actually, yes, the cost depends on the state through this map F. Basically, this F is defined on the social state, and it spits out an n-dimensional vector, n being the total number of strategies combined over the populations. As a simple example, in congestion games, you can create this cost as follows. You see the figure at the bottom. So x is a vector of fractions or the flows per routes. Then we multiply this with a routing matrix, which shows which route is implicated in which link. Okay, so when you multiply R and X, you basically get the aggregate flows per link. Okay, and then for each link, you have a delay function. Depending on what the flow is on that link, it will be longer or shorter to make it through that link because congestion starts. So each one is an increasing function that relates the flow to the time it takes to go through that link. So we denote this with phi of z, z being the vector of link flows. And then if you multiply this phi with the transpose of the routing matrix, that will translate back, that will just add up the travel times on each link, and it will give you the total travel time for each route again. So basically from route information X, we went to link flows, and from there we went back to the travel time per route. Okay, so that's the structure of F in the case of congestion games. The standard definition of Nash equilibrium for congestion games or for population games or monatomic games is given by the variational inequality you see at the bottom. And the interpretation is the usual one. If you were to take a small number of users from one strategy and move them to another one, a small fraction that will, so that the cost F will not be affected that much, then those drivers will not be better off with that switch. So that's the interpretation of that variation inequality. A couple of special types of games give us much more structure to work with. For example, potential games are those where the cost function is the gradient of some potential function little f. And an important fact is that when the little f is convex, then the Nash equilibria are the minimizers of little f over the social state space. Okay. An important implication of this is that we can find Nash equilibria by basically solving a convex optimization problem, which is extremely convenient. Okay. Now, if you go back to congestion games, they are potential games. Why is that? Because you recall this structure. And if I define the little f to be the sum of these so-called Beckman potential functions, these are basically integrals of the delay functions. Okay. So you can easily show that if you take the gradient of this sum, you're going to get the cost function f. Okay. So the Beckman potentials are convex because the delay functions are increasing. So you're integrating an increasing function, it will be convex. So that simply means that I can find Nash equilibria by minimizing the sum of the Beckman potentials. And that's extremely convenient, as I will explain in a couple of minutes with some applications. So, but already this very simple observation tells us some important things. It first tells us why Nash equilibria can be inefficient. You would like, from a overall perspective, from a social perspective, to minimize the total travel time for everyone. And the total travel time can be expressed as the sum of the flows on each link, the sum of flows times the time spent on each link, right? Overall links. And that's what you see at the top. But to find the Nash equilibrium, remember, we just minimize the sum of the Beckman potentials. So these two sums are, in general, not the same things, or minimizing them is not the same thing. Very simple example that's usually attributed to Pigou, who was the chair of economics at Cambridge at the turn of the century, more than 100 years ago. So in this example that's attributed to him, you have two routes from one origin to destination. The flow on one is x1, the flow on the other is x2. The assumption is that the first route on the top is a bit of a detour, but you have so much capacity on that road that the travel time is, say, 1 hour, no matter what fraction of vehicles are taking that. So it doesn't congest. The second route, on the other hand, is shorter potentially, but it congests easily, it's narrower. So in the extreme case where all of the users take that route, that also takes an hour. But if fewer took it, then it would be prorated. Okay. So if you work with these delay functions, then the potential functions we get are what you see in the middle, right below the capital Phi's. Okay, their derivatives match the delay functions. So then the minimum of the sum of these potentials, the Beckman potentials, is where the Nash equilibrium is. And you can see that that happens at 0, 1. The Nash equilibrium is the point where everybody is taking the normally shorter route, which is no longer shorter when everybody takes it, okay? Whereas the optimal for everyone, the social optimal, would have been half and half. If you could convince half of the drivers to take the longer route, then it would take 3/4 of an hour on average, but half of the population would have to suffer an hour drive while the other half spent only half an hour. So how do you convince the drivers? So naturally, that's not a Nash equilibrium. Okay, so a simple example of how we use the potentialness of the game, of the congestion game in practice. So in this study, we looked at a network from the Montgomery County in Maryland, and we asked whether we may not be able to detect routes that actually do not help with total travel time. Are there any routes that cause an actual Bayes paradox? Or at least are there some routes that we can eliminate, if we could eliminate, would not appreciably change the total travel time. And if those are routes that pass through, quiet neighborhoods and things like that, maybe and if they are not helping overall, maybe, the cities should do something about discouraging them. So in this study, to detect such routes, we do a greedy optimization for removing links and routes. And of course, for each choice, we need to know what the total travel time is. And for that, we need to know the Nash equilibrium. So to compute the Nash equilibrium quickly, we use convex optimization, knowing that the game is a potential one. Okay. Here's another application. This one is about choosing locations for charging stations. I just saw not an article, but a newsletter of some sort from Cornell just a few days ago, mentioning how important the placement of charging stations is for their profitability. So that already makes the case for this study. So we're asking, suppose you want to place, 3 or 4 charging stations in a city, and what are the best locations? Best in the sense of not adding to congestion. We're not looking into differential pricing or different price or something. We assume the pricing is the same, but we're asking, if you put it far out, then this will cause a big detour for vehicles that have to charge. and that will increase total travel time. That's not good. If you put it in the middle of the city, perhaps everybody will have to go there and create congestion where it didn't exist before. So now drivers who don't have to charge will also suffer. So that may again increase total travel time. So what is a sweet spot, or what is a good set of locations? So again, we do a greedy optimization for the location. We try out different locations one at a time. That's what I mean by greedy. We put one and then commit to the next and so on. But again, for each location, we have to find the Nash equilibrium. So we can evaluate the total travel time under that choice. And again, to be able to solve that, we use convex optimization. In this case, the game changes a little bit because there is also the factor of how much you spend at the charging station. We also model that as a link, as a self loop from the node where the charging station is located back to itself, and we associate with it again a delay function, meaning that if more vehicles are queued up to charge, it will take longer to get through that. But the potential structure of the game remains, and we take advantage of that to locate Nash equilibria efficiently. Okay, so that was about potential games and why they are useful. And another class that arises very frequently is the so-called monotone game. So these are games where the cost function f has this monotonicity property you see at the top. Okay, and there's an easy way to determine whether or not a game is monotone. You can just look at the Jacobian matrix. And if the symmetric part of the Jacobian matrix is non-negative for vectors z that are restricted to the tangent space of our social state space, okay? If that's non-negative, then you'll have this monotonicity property for vectors x and y restricted to the state space. Again, congestion games are also monotone. So that's why people, I guess, like congestion games. There's so much structure in them. They are potential games. They're also monotone games. It's relatively easy to see. We already know the structure of the cost. If you look at the Jacobian, you're going to have this R transpose and R on the two sides. R, remember, is the routing matrix. And then you'll have a diagonal matrix, including the derivatives of the delay functions, but we know those are going to be non-negative each, right? Because the delay functions are increasing. So this implies the monotonicity of the map F for congestion games. So we'll use that. We'll come back to this monotonicity property, but first a few words about evolutionary dynamics. So now we're not looking at a static game. We're assuming that every now and then the user gets a chance to revise its strategy, okay? Using certain learning rules, and those are rules that don't necessarily require too much information. It could be as simple as, looking at all the other options, comparing your current choice with respect to them, and picking one of those that give you a better choice or a shorter, smaller cost, with a probability that's proportional to how much better they are, right? So things of that sort, limited information rules. Okay, so the way this is done is you actually assume the users are probabilistically switching from one choice to another according to a probability that's determined by the learning rule. But what is done is you aggregate those, and you get a continuous dynamical model that describes how the evolution of the distribution over different strategies evolves over time. Some simple learning rules. One is the MJ Smith rule. In this case, you're just looking at, this gives you the flow rate from J to I. So you look at what your current cost is. I'm sorry, from I to J. You look at what your current cost is, that's pi I. You compare it to the others, and you switch to J with a probability that's proportional to how much better J cost is, how much lower. Another rule is one associated to Brown, von Neumann, and Nash, BNN rule. Here you look at the average cost. That, of course, requires a little more information. You need to know what fraction is using which to find the average. And then you compare that to what you're currently using. That's pi j. Okay, so I think I misspoke. These are rates for switching from j to I. Okay. All right, so given those rates at which users are switching from one to the other, we can write an evolutionary dynamic model that looks like the one at the bottom. So the first term, so this equation is telling us the rate of change of the fraction of users using strategy I, right? The increase in that will be due to users switching from J to I. So we sum over all J, all in the strategy set, of the product of xj and the rate at which people switch from J to I, okay? And the decrease in xi will be due to those that are switching from I to j. And that's going to be represented with the second term that appears with a negative sign. So that's the structure of the evolutionary dynamics model. And you have one such equation for each strategy I. Okay, so that was the evolutionary dynamics model. The input to that model is pi. That's the cost, right? But the cost itself depends on x through f of x. So we basically close the feedback loop. So x is an input to f, the price or the cost pi comes out, and that becomes an input to the evolutionary dynamics model. By construction, the vector field in the evolutionary dynamics model lives in the tangent space. In fact, the tangent cone to the simplex. So that means the trajectories will not leave tangent cone. That's a good sanity check for the validity of the model. Okay, and two basic assumptions. One is not necessarily satisfied for all learning rules, but satisfied for many of them, including the BNN rule that I mentioned and the Smith rule. So the first one is Nash stationarity, which means that if the right-hand side of the evolutionary dynamics model vanishes, that implies that the point you're at, x, is the best response to the cost defined by pi, okay, and vice versa. So the vector field vanishes if and only if x is the best response to pi, okay? Once you plug in f of x for pi, that simply means that the dynamics stop. You're at a rest point, at an equilibrium point in the sense of dynamical system. So let's call it rest point, okay? If and only if x is a Nash equilibrium. Okay, so this is meaningful and reassuring, meaning that the evolutionary dynamics will stop evolving if you're at a Nash equilibrium, because nobody benefits from that, right? All right, so then given this fact, we will take that as an assumption and we'll ask, okay, we have any rest point at the Nash equilibrium, but do trajectories starting from elsewhere converge to that Nash equilibrium? Okay, and this is not guaranteed in general. There are many examples of periodic orbits and even chaotic attractors. So many of them are illustrated in this book by Bill Sandholm that was published in 2010, a great book on population games. So why do we care about convergence? If we can prove that we have convergence to Nash equilibrium, that in a way justifies studying equilibrium without paying too much attention to the dynamics, right? And many results in the literature just look at static games. They explore properties of the Nash equilibrium, assuming that you will operate at Nash equilibrium. But that's not a given. So here we're showing that simple learning rules can take you under some conditions to Nash equilibrium, which justifies the equilibrium play assumption. Another important feature of this study is that once you can show you're converging to Nash with some of these learning rules, and remember, those learning rules do not require a lot of information. You only need some myopic learning rules. So if you can prove convergence, that also relaxes strong information requirements that are usually associated with operating at Nash equilibrium. One of the criticisms of Nash equilibrium is, how do people have so much information to be at the Nash equilibrium? But this is showing you that you don't need that much information. You can just do incremental improvements over time and that will take overall everybody to the Nash equilibrium. Okay, but again, this is not guaranteed. So this is a somewhat technical result rooted in control theoretic tools. So you can tune out if you're not interested in this, but I have a couple of slides on this. So for a large class of EDMs, evolution dynamics models, including BNN and Smith rules that we discussed, they have the following property. You can find a function of the state x and the cost pi, the price pi, that have the following properties. That function will vanish if and only if the right-hand side of the evolutionary dynamics model vanishes. In addition, the trajectories of this function, the derivative of this function over the trajectories of the evolutionary dynamics model will have the following dissipation inequality, which looks a little weird at first, but we'll interpret that. Or first we'll see why that's useful if that property exists. And here sigma is a term that's non-negative, so that's the dissipative term. Okay. And furthermore, we assume that that term becomes 0 again when the EDM vanishes. Okay. So why is this useful? It is useful if that property is useful, if it exists, and we'll see shortly that it does exist very often. If you have this property for the evolutionary dynamics model, and let me go back, and this is a property of the upper block in this feedback diagram, right? And if the lower block, which is the cost function f, has this monotonicity property that we already discussed, then the x dot transpose pi dot term you see at the top will drop out. Because of the monotonicity property, the inner product of x dot and pi dot will always be non-negative. Therefore, that negative term will only take away. And that's illustrated with very simple math about derivatives and taking into account the monotonicity property, which simply means that under the condition that the cost is monotone, the function s we see at the top actually serves as a Lyapunov function. It vanishes at the rest point, which is at the Nash equilibrium under the Nash stationarity assumption, and it's decreasing otherwise. Okay, so that means the trajectories of the evolutionary dynamics will converge to Nash equilibrium. Okay, so the core ideas of what I mentioned are actually in a paper by Hofbauer and Sandholm. Okay, maybe it's stated slightly differently, but our colleague Jeff Shama and probably a former student Fox interpreted this as a control theoretic passivity property. Standard passivity involves an inner product of an output and an input. In this case, we interpret pi as an input and x as an output, but we don't have the inner product of the input and output, but we have an inner product of their derivatives. Okay. For that reason, they call this a delta passivity property. It's a passivity property from the derivative of the input to the derivative of the output, as you see in the block diagram in the middle. Okay. So in the publication at the very bottom, we actually expanded this concept, and we identified other types of games that don't have the delta passivity property, but broader dissipation inequalities and corresponding variations of monotonicity properties. Okay. So to summarize what I discussed, if the evolutionary dynamics model has the Nash stationarity assumption and the delta passivity properties, which is the existence of a function s with this property, if the payoff is monotone, then you'll have convergence to Nash equilibrium. Okay, it's relatively easy to extend this to multiple populations. So basically now the function s will be a sum of the functions for individual evolution dynamics models. Okay? Now, if each of these evolution dynamics models for each population has the delta passivity property, we can make a weighted sum instead of just directly summing them up. Okay. And the overall dissipation inequality for the sum, the weighted sum, now looks as follows. So by adding these weights, I modified the inequality a little bit. Now between x dot and pi dot, I have W entering, W being a diagonal matrix incorporating the weights I used in S. What I know is that this dissipation inequality will be true no matter how I select those weights, W. So therefore, for any W with this structure, I'm going to have a corresponding property. So here I basically use the decoupled nature of the evolution dynamics models. Of course, eventually they get coupled through the cost function f, uh, to say a little more than delta passivity. This is a sort of a weighted type of delta passivity. And this is true for any set of weights. And I'm going to take advantage of this generality on the next slide. And here's an illustration of what we can do with this. So we're going to look at a congestion game with mixed autonomy. So we assume we have two types of vehicles, regular ones and autonomous ones. Okay. As you saw in the slide with our platoon demonstration, autonomous vehicles can keep a shorter headway than regular ones. I showed you we can maintain 6 meters even at high speeds safely. Regular vehicles will not do that. It just feels very uncomfortable to be 6 meters away from the car ahead. So, but the implication is that autonomous vehicles can also be more efficient in terms of using the infrastructure, right? So their externality is less. So here's a simple modification of the standard congestion game to account for this. That's due to my colleagues, Negar Meir and Roberto Horowitz. Negar was a PhD student at the time, and then she went to UIUC and she came back as an assistant professor in mechanical engineering here. So in this model, you split into two populations, autonomous and regular ones. Their externality is different. You discount the externality of the autonomous vehicles by a factor mu that's less than 1, between 0 and 1. Okay? And then you generate an effective flow. You add the contribution of the regular vehicles, and you add a discounted contribution due to the flow of autonomous vehicles, and you consider the sum to be the effective flow because you know that some of those vehicles will move in a more concentrated way, more compressed way. And you apply a delay function to that effective cost. Okay, and that gives you the total travel time per link. To generate the total travel time per route, again, you have to multiply by R transpose. Now, whether your externality is high or low, you're going to be subject to the same travel time if you're traveling on the same road. So the cost for autonomous as well as the regular vehicles are the same. They are R transpose times the vector of delays per link. Now, if you look at this modified game, you will see that it's no longer monotone in the traditional sense. If I look at the Jacobian, I'm going to have these R and R on the left, the non-negative matrix of derivatives of delay functions in the middle. But now on the right, I don't have R and R as I did before. I have mu times R in one entry, and that breaks the symmetry here, and you no longer have the monotonicity property you had before unless mu is 1, and that's not the interesting case. We are interested in mu less than 1, right? Okay. So f itself is not monotone, but we can see that W times f is monotone, W being a matrix that includes the factor mu. It's a very simple tailoring of the Jacobian, right? Once it's multiplied by W, the mu will appear on the left-hand side as well. We restore symmetry, and we have non-negativity of this matrix again. This implies that W times f of x is a monotone map. Okay, and with that, since we have the complementary property for an arbitrary W, right? For this particular choice of W involving mu, we still have it. So that means we can use the same tool to ensure convergence. Okay, so the moral of the story here, even though we don't have a monotone game, we have a weighted monotone game, and that's still okay for convergence to Nash equilibrium. Okay, with that, I'll start concluding. So we looked at integrating vehicle, road link, and network level controls. I showed you snippets of results from each layer, as well as their connections. For example, the Platoon demo was a connection of road link level control and vehicle level control. An important thing that you're all aware of is that we have a lot of new research opportunities with automated vehicles. Platoons increase capacity. We saw how that works. And there are also things you can control for modulating traffic, right? So now you have new knobs to tune in a way. So you can change the headway of autonomous vehicles and their speed if you have control over changing their speeds, and use that to modulate or to regulate the overall traffic. Lots of open problems too. The traffic models we used here are the standard ones that are used for congestion games, but they have shortcomings. They assume the delay on each route depends only on the flow on that route. But of course, if we have backups and so on and so forth, downstream traffic will also affect travel time. So those are not accounted for in the model that I just showed you. So we talked about convergence to Nash equilibria for finite strategy sets. We've been able to extend this to infinite strategy sets in the reference 17 at the bottom. So imagine a situation where you don't have discrete strategies, but a continuous one, like how much you're investing or what time you're leaving your house, right? That's a continuum. So similar convergence tools can be developed in that case. So the evolutionary dynamics model is sort of a diffusion approximation of a lower level model where individual drivers are basically flipping a coin to determine which strategy they switch to. It's a bias coin. If the cost is lower, there'll be a higher probability of switching to that, right? And the assumption is that there is a process, stochastic process, that determines when you make a switch from your current strategy. Every now and then you wake up and you decide to look at other options, okay? The standard assumption that leads to the evolution dynamics model is that there's an exponential distribution of the inter-revision times, okay? But this assumption is not always validated in real traffic data. People have shown that airline distributions may be more appropriate. So in recent work, which we are actually continuing, we have some newer results on that end. We're looking at modifying the evolution dynamics model, adapting them to airline distributions rather than exponential inter-revision intervals. Another line of work is combining the evolution dynamics model with physical dynamics, and then study the resulting equilibria that involves both users' choices and the physical dynamics, such as queue length and things of that sort. So the queue models could be incorporated in these dynamical system models, and convergence could be studied in combination. So we have a CDC 2024 paper that gives a sample of this line of thinking. All right, with that, I think I will stop and take any questions.
Thank you, Dr. Arcak, and we'll wait for some time for people to ask questions, and if there are any, I'll just relay them to you. Meanwhile, I have one question. It's related to the evolutionary dynamics model. Perhaps perhaps the Erlang clocks and that theory captures this. But I was wondering, let's say there is some inherent nature to humans of a particular population. Let's say like a so like someone could be conservative, someone could be just risk neutral and just take a decision based, be more myopic. So a conservative person would want to wait for more number of iterations to switch their strategies. Like, how is this, or like, is this being captured by uh, the evolutionary dynamics models? Is that, yeah, that's my question.
Yeah, that's a very interesting question. So, I mean, even the same distribution with different parameters, right? Could lead to different dynamics. Yes, that's a very good question. I want to say, although I can't prove it right away, that you can probably get similar results. You just have to have, you will have to, even if they have, okay, even in an original formulation, you're talking about a population, users in the same population. They have same origin, destination, and same everything, right? You can still split them into different population based on their um, revisions, right? I mean, how often they revise, right? And you can study the problem that way. The dynamics will change, but you'll create more of these boxes here. You had P populations here, right? Some of those that were lumped into one population, you would have to split it into subpopulations now based on their revision times, right? And you would get different dynamical models for each. But I do think that the main results would not be affected. But that's a great question. Yeah, something that needs to be explored.
Thank you. And perhaps there's one more question, like
Mhm.
going back to the state abstractions. Just a second.
Yes.
Like finite state abstractions and
Mhm.
having this logic, uh, and all of this. Like, uh,
Yes.
what if there was a human driver, or like in a mixed traffic situation, you would want to predict how a human driver would behave, and then adapt that into the state discretization, and considering all of these reachabilities and safety guarantees. How should one approach?
Mhm.
How should one go about that in this sort of situation?
Right. So, I mean, this is a very general formulation where you take a dynamical model and, try to represent it as a finite transition model, right?
Yes. Yes.
So how you incorporate human actions into that, I'm not quite sure if I can answer that immediately.
Okay.
I mean, you mean in the sense of the human having a say in what U is?
It's more like if there is a human driver, and a
Hmm.
human driver could be, let's say, conservative, and it could yield to the autonomous vehicle.
Right.
And if it was a rash driver, the human driver may not yield to the autonomous vehicle.
Yes.
And
So
you
I
could,
guess what you could do is you could build into your dynamics what you expect from the driver. I'm not sure how I would do that, but then what's shown as U here would be the intervention by the autonomy features, right? And now your objective now would be to perhaps keep it safe while interfering as little as possible, things of that nature, right? So is that do you follow what I'm saying?
yeah,
So,
yeah,
but if you had a model of how the user behaves, right? I mean, then you could do this. But otherwise, if you have variations in the user behavior, actually, now that I think about it, I don't think it's I think it should be doable because you can over approximate. So essentially, what you're doing in the finite state abstraction is over approximating the behaviors of the dynamical model, right? So when we decide whether a transition is happening from one bin to the other in the state space, right? We are accounting for all possibilities. That's what reachability analysis does, right? In fact, we account for things that also may not happen because with reachability analysis, we are finding an outer approximation. So we create transitions that may not happen in reality. So the funnel of behaviors that are possible under a set of drivers can actually be, it should be possible perhaps by using data to incorporate into the transitions. It's not something we've done, but it could be done. And then you could be treated as the autonomous actions or the automated ADAS types of features that interfere when the driver is headed in the unsafe direction.
thank you.
Yeah, it's another interesting question.
Yeah. Um, so I don't think we have questions from the stream.
Okay.
Yeah. And this.
You can always reach me by email. It's the last name at berkeley.edu, and I'll be able to answer by email. And
Thank you
thank
so
you for
much.
listening.
Yeah. All right, Dr. Arsak. Thank you for giving a talk
Okay.
at our seminar series, and
Okay.
hopefully we'll meet someday on similar research at some point.
Yes.
Yep.
Okay. Wonderful.
Yep.
Okay. Thank you, everyone. Bye.
Uh, Thank you everyone for attending the talk. We'll see you next week. Bye bye. Thank you, Dr. Arsak.